Hi, dear students, I am Dr. Rajiv Sapre. This is lecture number 50 about metric topology. I will appeal all of you to subscribe my channel Maths Made Easy by Dr. Rajiv Sapre. There is a playlist for these lectures on metric topology. You can refer all these lectures and you can put your comments, your suggestions. Subscribe my channel. So now currently we are discussing on sequences of metric spaces. In the previous lecture we have discussed lot of things. What is convergent sequence? See, that we have discussed in previous lecture, that what is convergent sequence, right? These are the things that we discussed. Convergent sequence, definition, etc. we know. Convergent sequence. Secondly, we studied what is bounded sequence. Also, what is the relation between these two? That means whenever sequence is convergent, so convergence, we can say, implies boundedness. Implies boundedness. When sequence is convergent, it is bounded. Is the converse true? We have said no. We have produced an example also, that bounded sequence need not be convergent. Okay. Now in this lecture, I will be introducing another idea called subsequence, and then it is very obvious that whenever sequence is convergent, subsequence is also convergent, and it converges to same limit to which the main sequence converges, right? So what is subsequence first? Subsequence means what? As it is subset, as it is, there are many times we have said something like this: subset, subgroup, subring, subspace, etc., etc. So the word sub is there. So you have a main sequence, then only you can think of subsequence. Instead of sequence, you cannot think of subsequence. This is obvious. Instead of set, you cannot think of subset. Instead of group, you cannot think of subgroup, right? So subsequence is a sequence in its own right, but the terms in the subsequence are, whenever you consider it as a set, then it is a subset of the set formed by terms of the sequence. For example, see, suppose I take a usual example we will take to understand the idea of subsequence. Suppose you have R comma D metric space, right? Usual topology. And suppose I talk about the sequence 1 by n, right? Suppose this is my sequence xn. Xn is 1 upon n. That means this sequence I am talking about, xn. Xn is 1 upon n for all n belonging to capital N. Now you know what are the terms of this sequence. They are 1, 1 upon 2, 1 upon 3, 1 upon 4, and so on. 1 upon n is the general term. We know this. This is a sequence. Now what you do is take the terms of this sequence with certain sequence. हा जो शब्द आहे त्याच्यामध्ये काहीतरी ऑर्डर दडलेली आहे. कुठल्याही टर्म्स घेऊन माझा सबसिक्वेन्स नाही होणार. What I should do is, see now, suppose I take all the terms with even suffix. That means I consider the terms x2. What is x1? x1 is 1, x2 is 1 half, x3 is 1 by 3, like that. Xn is 1 upon n, right? So if I take x2, x4, x6, etc., general term will be x2n. Now this is a subsequence. This is a subsequence of xn. That means what? I will take the terms 1 upon 2, then 1 by 4, 1 by 6, and so on. General term will be 1 upon 2n, where n belongs to a natural number. See, this is a subsequence. Subsequence is a very important concept. Actually, what we are doing is, you know that whenever I say that xn is a sequence, right? What do you mean by this? There is a function f from the set of natural numbers to x. This is a function from set of natural numbers to x. What you do is you take another function g from say n to n, which is monotonically increasing. Monotonically increasing. monotonically increasing. monotonically increasing. Now what you know, this is the function from n to n and this is a function from n to x. So I can make the composition of these functions, right? What can be that composition? It will be g circle f or f circle g. It should be f circle g, right? So consider f circle g. Now see, g is a function from n to n. So whenever you operate this f circle g on say n, what does this mean? F circle g of n means what? It is f of gn. Now g is a function from n to n. So this is legal. This is an element of n, and on that I can operate f because f is a function from n to x. So this f circle g from n to n, this is okay na, f of gn, right? That is, we can say f circle g is a function from set of natural numbers to x. So this is also a sequence because we know domain, a function whose domain is set of natural numbers is a sequence. This is what we know. Here is a function whose domain is set of natural numbers and the codomain is x, which is a metric space, correct? So what I can say, that if you have a sequence in x and if you have a monotonically increasing function n to n, right, then you can think of f circle g from n to x. So this f circle g is a sequence. F circle g is a sequence. Why? Because its domain is set of natural numbers, right? So this sequence, right, that means what? Sequence corresponding to f circle g is a subsequence. It is a subsequence. I hope you understand. I will give one example of this. What is actually happening? See, you continue with the same definition, same sequence. You take R comma D, usual metric space, okay, and then let xn is equal to 1 by n for all n belonging to capital N. So this is the sequence we know, right? So this is a function now. What do you mean by xn is 1 upon n for all n belonging to capital N? It is a function f from n to x, n to r here. And definition of that function is f of n is 1 upon n. Now let g be the function from the set of natural number n to the set of natural number n defined by g of n is equal to say 5n, right, for all n belonging to capital N. You can easily see that this is monotonically increasing function. G of 1 is 5, g of 2 is 10, g of 3 is 15, g of 4 is 20, etc. See, g of 1 means what? You are putting n is equal to 1 in this definition, so it is 5. G of 2, what is it? It is 10. G of 3, what is it? It is 15, and so on. So what is happening? When the terms are increasing, functional values are also increasing. So this is monotonically increasing function. Now what you do is, consider the composition f circle g. F circle g will be the function definitely from n to r. Why? Because your g is a function from n to n, we are operating it, and on that f is being operated, outcome will be in r. R means this real line. So this is n to r, and any function whose domain is set of natural numbers is a sequence. So this is also a sequence. But now what will be the terms in this sequence? Right? Terms will be f circle g of 1. Right? So see, terms will be terms. F circle g of 1 means what? It is f of g1. But what is g of 1? It is 5. So this is f of 5. So it is 1 upon 5, because f of n is 1 upon n. Our definition, f of n is 1 upon n for all n belonging to capital N. Similarly, if you talk about f circle g operated on 2, it will be f of g2. F of g2 means what? F of 10, because g2 is 10, as you know. So this is f of 10, means it is 1 upon 10. Now you can continue this. You can continue this. So what happens here? whenever I collect the terms of this F circle G sequence, what I get, which terms I get? So we get a subsequence, what subsequence we get? 1 upon 5n, we can say. This will be the general term of that sequence, because the terms of this sequence are 1 upon 5, then 1 upon 10, then 1 upon 15, and so on. See, all the terms of the basic sequence we are not taking. All the terms when you take, it is also a subsequence, because definitely, right, it is a function, monotonic function actually. Monotonic increasing is not needed actually. You can say just monotonic function. Right, that is okay. But see, whenever I want to get, means आपण कधीही काय म्हणतो बघा, कुठलाही सेट घेतला की त्याचा स्वतः ट्रिवियल सबसेट आहे. एम्प्टी सेट हा ट्रिवियल सबसेट असतो, नॉन ट्रिवियल वी आर इंटरेस्टेड इन. सो नॉन ट्रिवियल सबसिक्वेन्स whenever I want to have, I should have a monotonic increasing function. ठीक आहे. मुद्दा काय आहे की सबसिक्वेन्स म्हणजे काय हे त्याच्यामधून मी तुम्हाला सांगण्याचा प्रयत्न केला. राईट. So there are many different what we can say references. When you use, you will find various ways of defining subsequence and all that. So this is a subsequence. In short, it is the terms in the subsequence are, whenever you consider the set formed by the terms in the subsequence, then what happens? It is a subset of the range set of the sequence. So range set of subsequence is a subset of range set of sequence. This is what we can easily observe. आता पुढचा मुद्दा असा येतो की what about convergence of the subsequence? So I leave this as an exercise to you. Very simple. The thing is, this is the theorem. I will ask you to write the proof. Right? If sequence xn of metric space x comma d is convergent and converges to x, then the subsequence say xnk of xn is also convergent and converges to x. So what do you mean to say by this result? That sequence, if it is convergent, if the sequence is convergent, then we are talking about subsequence is also convergent and converges to x. See, mathematics, always I have said, it is a precise science. What you mean by that statement is fixed. We are nowhere claiming that if the sequence is not convergent, subsequence is not convergent. Nothing of that sort we are claiming. You can give examples of the sequences which are not convergent but their subsequence is convergent. Okay, but whenever sequence is convergent, sure shot its subsequence is convergent and it converges to same limit to which the sequence converges. This proof is not difficult. You can try this. Basically, what we are doing, whenever you say sequence is convergent, it means what? From particular term onwards, all the terms are near to x. That k, we are saying, there exists k belonging to some natural number, such that for all n greater than or equal to k, distance between xn and x is less than epsilon. What it means? It means from particular term onwards, all the terms are near to x. Now, whenever I talk about subsequence, right, the terms of that subsequence are again from the x, again from the main sequence xn. So same story will happen here. Only thing is that it may be, see, in the main sequence that k may be 100, but in subsequence it need not be 100. It can be 4th term also. It can be 10th term also. Depends on what subsequence we are taking. But then that term onwards, because the terms in the subsequence are terms from the sequence itself, and so it follows. So I leave this as an exercise to you. But now what about, so try this. Whenever I leave this as an exercise, means you should try that, right? You should try that. All the results you should write, all the theorems, whatever exercises I have given, you should try those exercises. Refer some textbooks, refer some reference books, find the corresponding material and write down the proof in your own language. This is very important. Writing the things in our own language is very important. If you have understood the subject, this can be easily done. Otherwise, you have to take a lot of efforts to write down the mathematical material, right? You should write that. Okay. Now, what about the converse of this? That means what? Subsequence is convergent. Does it imply sequence is convergent? No. Surely, because you have this sequence, very simple. So each converse true. Each converse true. Here what we have proved? Sequence convergent implies subsequence convergent. But if subsequence is convergent, does it imply sequence is convergent? We are saying no. And now you know many results we have proved. This is 15th lecture that is going on. So in all the previous lectures, many times I have said that whenever you want to say no, then it is sufficient to give counter example, or that example is called counter example. So you produce an example, is converse true, the answer is no. That means what? Subsequence is convergent. Subsequence is convergent does not necessarily imply sequence is convergent. And to prove this, you can give usual example, -1 raised to n. This is sufficient. We know -1 raised to n sequence is not convergent. This also you prove. Prove this. How you will prove? -1 raised to n, this sequence is not convergent. Prove this. Means, see, whenever you want to prove -1 raised to n is not convergent, you have to assume contrary. Or you use any method. It is not necessarily that whatever method I prefer, you will prefer to prove that result. But if I want to prove this is not convergent, you assume it is convergent and come to some contradiction. If -1 raised to n is convergent, what will happen? Think about it. This proof is given in one of the lectures by Dr. S.K. Ray. Nicely he has given the proof. You can find on YouTube, Dr. S.K. Ray. Right? I will like you to go through that proof. And in, I don't know which lecture, first, second, third, I don't know where he has started convergence of the sequences. There he has given this proof. But it is nicely given. You can try to understand that and write it in your own way. Don't just copy what he is writing on the whiteboard. You should understand what is being done and write it in your own way. Okay, so I leave this as an exercise to you. All these exercises that I am leaving for you, you should work on them. Okay, so -1 raised to n is not convergent. But if you consider -1 raised to 2n, or if you consider -1 raised to 2n minus 1, these are two subsequences. -1 raised to 2n means what? It is -1 raised to 2, then -1 raised to 4, then -1 raised to 6, etc. General term is -1 raised to 2n, and so on. So whenever you consider this sequence, it is nothing but a singleton 1, which is this is a constant sequence, so it is convergent. Same story for -1 raised to 2n minus 1. When you put n is 1, this 2n minus 1 is 1. So this will be, means when you talk about that, it will be -1 raised to 1, then -1 raised to 3, then -1 raised to 5, and so on. Then -1 raised to 2n minus 1, and so on. This is just a -1 term, and as this is also a constant sequence. So what has happened? We have considered two subsequences of the sequence which is not convergent. -1 raised to n is not convergent, but these two sequences are subsequences of this sequence, and they are convergent, right? So this is example which is sufficient to prove that converse of this result. Which result? Whenever you are given a convergent sequence, then its subsequence is also convergent, and where it converges to the same limit to which the sequence convergent. असं कधीही होणार नाही की सिक्वेन्स एक्सला कॉन्व्हर्ज होतोय आणि त्याचा सबसिक्वेन्स वायला कॉन्व्हर्ज होतोय वेअर एक्स इज नॉट इक्वल टू वाय. Subsequence will converge to the same point where the sequence converges. But when subsequence is convergent, it's not necessary that sequence is convergent, and this example is sufficient to prove that. Right? I hope you understand whatever is discussed in this lecture. Right? We will continue in the next lecture. Till then, see what are the things that are discussed in this lecture and try to write down the exercises. Try to do those exercises. Write down the proofs. And writing mathematical material has some method. It should be methodically written. Whenever other person reads whatever you are writing, it should be explanatory. That person should understand what we are writing. So writing mathematical material requires skill. You will acquire that skill by listening many good lectures from YouTube, like these lectures, and also reading through various reference material. Okay, so we will continue in the next lecture.